Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Edmund Halley's 2005 Synopsis Astronomy Cometically represents a pivotal moment in the empirical validation of Newtonian physics, a work whose profound influence arises from its direct and systematic application of gravitational theory to a class of celestial objects previously shrouded in superstition and interpretive ambiguity. The document functions as a monumental piece of computational astronomy, aiming to demonstrate that comets, far from being erratic omens, are in fact orderly members of the solar system, their motions governed by the same universal laws that command the planets. This essay will conduct a rigorous evaluation of the Synopsis core claims, proceeding section by section through its internal logic, assessing the evidence Halley marshalled, the methodologies he pioneered, and the specific arguments he constructed to reframe humanity's understanding of these transient celestial visitors. The purpose is to move beyond general praise and into a detailed examination of the intellectual machinery at the heart of this foundational Section 1. The theoretical foundation and parabolic assumption. The synopsis opens with a foundational assertion that comets move in conic sections, specifically ellipses, parabolas, or hyperbolas, with the sun at one focus. This claim is a direct consequence of Isaac Newton's law of universal gravitation, which posits that the force between two bodies is proportional to the product of their masses and inversely proportional to the square of the distance between them. Halley's initial and most critical methodological decision is to treat all cometary orbits as parabolas. He evaluates this choice by presenting it as a matter of computational practicality and observational sufficiency. For orbits of extreme eccentricity, the portion of the trajectory visible from Earth near perihelion is almost indistinguishable from a parabola, given the quality of historical observations. Attempting to calculate the precise parameters of a vastly elongated ellipse would introduce a spurious precision unsupported by the available data. Halley's claim, therefore, is that the parabolic model provides the most robust and honest fit to the observational evidence. He details a geometric method derived from the first book of Newton's Principia for determining the specific parabolic path of a comet from three distinct positional observations. The process involves a graphical and iterative technique to find the parabola that connects three observed points in space and time while adhering to Kepler's second law of equal areas swept out in equal times. The internal logic is compelling. He establishes a universal physical law, proposes a simplifying yet powerful mathematical model consistent with that law, and outlines a clear procedure for applying the model to raw data. The strength of this initial section lies in its intellectual transparency. Halley is effectively teaching his readers how to perform the very calculations that form the basis of his subsequent claims, building a shared framework of understanding before presenting his revolutionary conclusions. His argument is that this parabolic hypothesis is the key to unlocking the entire historical record of cometary sightings. Section 2. The assembly and analysis of the historical catalogue. Following the theoretical preamble, the core of the synopsis is presented a comprehensive table detailing the orbital elements of 24 comets observed between years 337 and 1698. The central claim of this section is evidentiary. By systematically applying his parabolic method to the historical record, Halley asserts that he has transformed a disparate collection of anecdotal sightings into a coherent, quantifiable dataset. The evaluation of this claim must focus on the monumental labour of its creation and the inherent challenges of the source material. Halley drew upon a vast array of historical astronomical records, from the medieval accounts documented by Nicephorus Gregoras to the more precise pretelescopic measurements of Tycho Brahe and the telescopic observations of Hevelius, Assini, and Flamsteed. His methodology involved a painstaking process of data filtering and reduction. For each comet, He calculated 5 key orbital elements: the longitude of the ascending node, the inclination of the orbital plane to the ecliptic, the longitude of the perihelion distance from the Sun in astronomical units, and the time of perihelion passage. The very act of tabulating these values for 24 comets constitutes a powerful argument for the universality of his method. The table itself claims that the apparent chaos of cometary appearances conceals an underlying mathematical order. A critical assessment of this section reveals Halley's sophisticated understanding of observational error. He acknowledges the varying quality of his sources, implicitly weighing the accuracy of observations made with naked eyes against those made with micrometers and telescopes. The internal consistency of the results derived from such heterogeneous data stands as a testament to the robustness of the Newtonian model. The claim is less about the perfection of any single calculated orbit and more about the collective power of the entire catalogue to demonstrate a single, unifying physical principle at work across centuries. Section 3. The argument for periodic recurrence. Within his table of cometary elements, Halley identifies a remarkable congruence. The claims in this portion of the synopsis become more specific and audacious. He directs the reader's attention to the comets observed in 531 1627 and 1682. His central argument is that these were not 3 distinct objects but rather 3 successive apparitions of a single comet travelling in a highly elongated elliptical orbit. The evidence he presents is the striking similarity in their calculated orbital elements. He points out their shared inclination of approximately 17 degrees, their nearly identical perihelion distance of about 1/6 of an astronomical unit, and their retrograde motion along the common orbital path. This claim is a profound inductive leap. While the parabolic assumption was sufficient for calculating the visible arc, explaining this pattern required positing a closed, elliptical orbit, signalling a comet's permanent membership in the solar system. He evaluates the main discrepancy in his own data. The interval between these and 1607 appearances was approximately 76 years, while the interval between these and 1607 and 1682 appearances was closer to 7 to 5 years. A lesser mind might have seen this as a refutation of the identity hypothesis. Instead, Halley makes a yet more profound claim. He attributes this variation in the orbital period to the gravitational influence of the major planets, particularly Jupiter. He argues that as the comet travelled through the outer solar system, its path would be perturbed by the gravitational pull of these massive bodies, slightly altering its velocity and thus modifying the period of its return. This is an extraordinary piece of physical insight, demonstrating a grasp of the gravitational n-body problem that went far beyond the idealized two-body calculations of the Principia. The claim is twofold. The comets are identical, their orbital period is variable due to predictable physical Section 4. The testable hypothesis and the acknowledgement of perturbations. This section of the synopsis contains its most famous claim and the ultimate test of its entire intellectual framework. Based on the identification of the recurring comet of 531 and 1607 and in 1682, Halley predicts its return. He states that the comet, which he now implicitly claims as his own, will reappear, reaching perihelion around the end of 1758 or the beginning of 1759. This is the culmination of his entire argument, transforming cometary astronomy from a historical, descriptive science into a modern, predictive one. The evaluation of this claim must appreciate its conditional nature and scientific humility. Halley is explicit about the uncertainties. He directly references the potential for retardation due to the gravitational pull of Jupiter and newly acknowledged Saturn. He writes with a certain academic caution, stating where the comet might be seen and confessing that he is unable to calculate the precise magnitude of the planetary perturbations. This acknowledgement of the model's limitations is itself a powerful scientific statement. He is defining the boundary of current knowledge and pointing toward the next great challenge in celestial mechanics, a full theory of planetary perturbations. The audacity of the prediction is breathtaking. It was a hypothesis whose confirmation he would be unable to witness, a true intellectual bequest to posterity. The claim's strength rests on its falsifiability. It was clear, unambiguous, and dated prediction that would either be verified, cementing the power of Newtonian gravitation, or would fail, exposing a flaw in the entire theoretical edifice. There is a subtle, almost wry, confidence in his tone, as he encourages future astronomers to remember that this discovery was first made by an Englishman. The claim is a synthesis of historical data analysis, physical theory, and a bold, forward-looking hypothesis. Its posthumous confirmation, Ioun Palachum Christmas Day of 1758, was the ultimate validation of Halley's entire project. Section 5. The Great Comet of 1680 and the boundaries of the parabolic method. In a further demonstration of intellectual honesty, Halley includes a detailed discussion of the Great Comet of 1680. This object held a special place in the history of science, as it was the very comet Newton had used to test and refine his own theories of cometary motion. Halley's claim regarding this comet is one of exceptionalism and pushes the boundaries of his own model. He calculates a parabolic orbit for it, but the data, particularly its extremely close pass to the Sun, suggests an orbit of immense period and eccentricity. The eternal argument here is a subtle exploration of the relationship between a parabola and a very long period ellipse. He speculates, at its orbital period, might be on the order of many centuries, citing a possible earlier appearance in the year 1106, and even connecting it to a comet seen at the time of Julius Caesar's death in 44 BCE. This line of reasoning serves a crucial purpose within the synopsis. It demonstrates that the parabolic method, while powerful, is an approximation. For comets with exceptionally long periods, the true elliptical nature of the orbit becomes significant, yet it remains computationally and observationally difficult to resolve. By grappling with the 1680 comet, Halley is stress testing his own framework. He is showing his audience of fellow natural philosophers that the Newtonian system can accommodate even these extreme cases. The claim is that the comet of 1680 is a member of the solar system, but one whose vast journey stretches the limits of contemporary mathematics and observational timelines. It is a masterful stroke, using a difficult case to reinforce the comprehensive power of his theory, while simultaneously acknowledging its present constraints. This adds a layer of sophisticated nuance to the work, showing that Halley was engaged with the anomalies and difficult cases, the very places where scientific theories are most productively tested. Section 6. The vision of a populated and dynamic solar system. The concluding remarks of the synopsis broaden its claims from the specific to the general, offering a new vision of the solar system's architecture and contents. Having established the periodic nature of at least one comet and the lawful behaviour of 24, Halley implies a much larger population. He speculates that there are vastly more comets and planets and that they travel in all conceivable planes and directions, populating the solar system in a way previously unimagined. This claim fundamentally alters the planar model inherited from Copernicus and Kepler. The solar system is presented as a teeming, three-dimensional space filled with bodies on stable, albeit highly eccentric, orbits. He further speculates on the physical nature of comets, discussing the formation of their tails as material driven away from the nucleus by solar heat, a claim that aligns with Newton's own thoughts on the matter. His evaluation of their purpose touches upon a popular, though speculative, idea of the time that comets might serve to replenish the vital spirits or moisture of the planets, including Earth. While this particular claim steps away from the rigorous mathematical demonstrations that precede it, it serves a rhetorical purpose. It integrates comets into a dynamic, almost ecological, conception of the cosmos. They are part of a functioning system, performing a role within the divine plan, a common framing in the natural theology of the era. The primary claim of this concluding section, however, is the successful annexation of the cometary realm into the empire of physical law. The work as a whole argues that the universe is not only orderly, but also knowable, through the combined application of mathematics and observation. In conclusion, a detailed evaluation of the internal claims of Edmund Halley's Synopsis Astronomy Chemetici reveals a work of extraordinary intellectual rigor and strategic brilliance. Each section builds logically upon the last, moving from a general theoretical principle to a specific methodological application, through a monumental display of computational evidence to a specific case of identity, culminating in a falsifiable prediction that served as the ultimate test of the Newtonian worldview. Halley's claims are powerful because they are so carefully scaffolded. His use of the parabolic assumption was a masterstroke of pragmatism, allowing him to render centuries of disparate data tractable. His argument for the identity of the Wisarden 682 comet, supported by orbital data and a prescient theory of planetary perturbations, represented a profound advance in physical understanding. The prediction of its 758 return was an act of supreme scientific confidence, a challenge issued to the future. Even his treatment of difficult cases like the 1680 comet served to reinforce the theory's power by honestly delineating its boundaries. Ultimately, the Synopsis' most enduring claim is its demonstration that the scientific method, as exemplified by Newton, could domesticate the most seemingly chaotic phenomena in the heavens. It transformed comets from objects of fear into subjects of calculation, proving that they were an integral, predictable part of a comprehensible and law-governed solar system.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.